Okay. In this week, we have talked about the Z transform, digital signal processing, and section 1 is related to Z transform. Okay. Firstly, we need to talk about the Laplace transform. Remember, Laplace transform that we have the frequency spectrum between the watt 0 to infinity, right? And then we can apply the any function in here with the based convolution pattern in terms of the exponential minus st dt, and then this returns to the what, the r frequency domain or the r frequency components. Okay, and so first of all, this is converting the what time domain to or into frequency one, right? One of them is that. And so we can treat the whole equation in algebraic form, or we can evaluate the results of these things in terms of the algebraic equation, s squared plus 2s plus 5, for example. And so we can check the roots, and then we can examine or assess the performance of our model or the transfer function. Okay, and so to obtain the characteristics of the system. Okay. But in discrete domain we have different properties. Okay, in discrete domain we have different features. Okay, first of all, in the continuous time domain, the dt or the sampling time is going to 0, but this is not satisfied in the what discrete time, and we have only to what the instant value at each step. Okay, we can select the dt as the 1 milliseconds or the 10 milliseconds, and then we can take the 1 points. Okay, and also the tt can be changed in discrete time. Okay, which means that we cannot use or utilize the what continuous theorems, because in the continuous theorem we have only deal with the what, with the area or the integral form of something, for example the function or the time dependent features. Okay, and so if this is the case, we have only sequence, right? This happens or occur when dealing with this domain. Okay. This is the basic feature for the what, for the discrete time domain. And so we need to another theorem, but we need to apply this theorem on the sequence, not the area form. Okay, and so we have, in conclusion, we have the sequence or the instant value instead of what, area form. Okay, and so how can we deal with the sequence one? We have the Laplace transform for what, for the continuous time system, but in the discrete domain we have the different sampling period, and also we have the one value, instant value, which means that we have sequence. And so in order to deal with this sequence, we have the Z transform. Okay, this is the purpose of the what, the hour theorem. Okay, and so this Z transform is applied on the what, on sequence value or the discrete time values. Okay, but in order to understand that, we need to give the what, the comparison, or we need to compare to what, this Laplace and Z transform. Okay, but first of all we should define the what, the theorem. Theorem 5.1 is written by the Z transform is order of discrete time signals x n. N is the index of the hour variable in here and is defined as to what, x z is the r basic notation in this transform, because in continuous one we have the s, but in this time we have z. Okay, and so this z is equal to x n parenthesis value in here, just like this one. And so if this is the sequence, and then n minus infinity to infinity value, and each of the sample must be multiplied with the what, with the z over minus n. Okay, and so what is the z in here? Z is the polar coordinates in the Euler identity formula. Z is equal to the what, the r e j theta, or which means that we have the r cos theta plus j times sin theta. Okay, and so in the graphical notation we have these nominations. This is the r basic theorem. Okay, and so we have 1 point in here. Okay, this is the polar coordinates, not the area is threaded in this domain. We have only what, only these things. And so how can we compare these two algorithms, Laplace transform and Z transform? First of all, we have Fs 0 to infinity value, ft times e st dt is the formula, and also this is the area, and s is defined with the what, the sigma plus j times omega, right? J times omega is only related to what, the frequency components, but this sigma value is related to what, the real part of this study, which means that this is the real root for the what, for this equation, and then we can grow or the decay the r signal ft based on this information. Okay, we can analyze it based on this thing. But in the Z transform we have the x z, which is given in this domain just like this one. X z is equal to n minus infinity to infinity value x n times z minus n, and so this is the line. Okay, in this domain this is line, but this is the area. Okay, and so how can we visualize this result? Z is equal to the r e j theta. Okay, and so this creates the what, the magnitude and the angle in the what, in Euler identity formula or the geometrical representation. But this is the s is sigma plus j dot creates the what, the growth or decay value or oscillation parts on these studies. Okay, and so how can we treat these values? For example, if we have this kind of Euler identity formula based on these things, just like this one, and then this S is related to what? The sigma and JW, and also this the sigma and JW, right? This is the Euler identity formula. And so this S can be compared with the what? With the area notation. We can only deal with this area. And so this area returns to the what? The frequency of these terms. But in the sequence, we cannot do that. Because in the sequence, we have just kind of information. This is the R, and this is the theta, okay? And so this is the angle, this is the magnitude of our algorithm. And so at each case, we have some specific points on this area, okay? And so we cannot fill the whole Euler identity formula in here. But in this domain, in the continuous domain, we can do that, okay? And so if we have the continuous signal, and then we can have the area. And so we can obtain the information from this area form. But in the discrete domain, we have the individual parts of this sequence. And then we cannot take the integral form of these terms. And so we need to what? Analyze this signal based on the what? The magnitude value and the angle value. We can just use that, nothing more. But in the continuous domain, we can evaluate our signal based on this information. This is the basic difference between the Laplace and the Z transform. And so the source of this difference based on the what? Sampling. Nothing more. Okay? You need to understand that. So in this case, we always minimize the area. Okay? In this case, we just use or maximize the points in here, because if we have a lot of points about the sampling or the system, and now we can easily control this signal, but we may not use that information because we can sample the signal at the 1 seconds or the 100 milliseconds or the 10 milliseconds, which is depending on the what? The application types, right? And so in some cases this is an advantage, okay? But in some cases we don't have the advantage. It's a disadvantage. But if we want to use the microcontroller or the microprocessor or the computer structure to evaluate your signal or the system, we should always utilize the what? The Z transform. Because the microcontroller or the computers is run based on the what? The sampling rate. For example, 4 gigahertz processor or the 5 gigahertz processor. Everything are the discrete in computer structure or in electric and electronic engineering. Okay? You need to understand that. So, another important term about the Laplace transform and Z transform is the what? Is the example notation. For example, S can be equal to what? The -3 plus 2j, okay? Or Z can be equal to 0.9 times E j pi divided by 2, okay? We can use these informations in here, okay? And so, how can we draw this signal in the what? In the Euler identity. Just like this one. If we have the region in here, and so we have 2 and -2 in here, okay? For this root. So this is the -3, or in another term, we have this root, and then we can, or we don't need to supply the complete Euler identity formulation because our system creates in the what? In the ellipse form, okay? or in this case we have, just see that, 0.9 magnitude in here, right? And so this is the pi divided by 2, 90 degrees, okay? We can say that, we can use that. And so how can we, minus this one, okay? And so how can we run or evaluate or the progress in time this signal? For example, if this is the -3, and so this signal must be goes to the what? The 0, because it's at stable pole, right? But at each time we can draw this signal just like this one. This is the first place, and after that we can small this signal just like this one, but the oscillation is always at the same time, right? In time we reach in the real plane to the what? To the 0 value, but the magnitude of this time is always preserved in this signal, okay? And so at each time we have this signal just like this one, okay? And after that we have the points, okay? T increase at each time in here. But in the Z transform we have different characteristics, because we have the 90.0.9 magnitude value in here, okay? And so this creates to the what? To this kind of output. It cannot be 0, but we can always to what? Closing just kind of output, right? And so in time we can build this kind of information. This is the 0 value, and so can always smalling right now, smalling and smalling and smalling values, and also we have the what? The 0 value in here in T plus plus. If we have the -0.9, and so at each time we can search the whole area just like this one, okay? This is the rock plane, okay? This is the stability rule for the Z transform, but I will talk about it, okay? But all the oscillation parts are constant in here, pi divided by 2 minus pi 2, okay? And so in this case we have the constant value 2 and -2, okay? This is the basic difference between to what? To Z transform and the Laplace transform, okay? Any question? Do you understand what I'm saying in here? The oscillation always happens in this kind of system because we have the frequency parts in here. This the J parts represents the oscillation, and also these parts represents the this oscillation, okay? Okay, if we have the 0 value in here, and so the every part is given in the what? In the real domain. And so we can, if we remove these parts in here, and then we don't have the any oscillation, we have just kind of signal, okay? But if we are utilizing to what? J, or which means that's the dynamicity of our signal or the systems, and then we always oscillate in this signal, okay? No, this is the R root for the S representation. This is not a function. This is the solution of the what? The S square plus blah blah blah, okay? And so this root is the one root. the other root is equals to what? The plus minus. Okay, just remember that this is a simple depiction to what the how our signal evolves in time based on this root. And so I show these terms to you for the what? For the represent the basic difference between the Laplace transform and the Z transform. Okay, in this domain we will deal with only with the what? The area form of these terms. The integral part generates the frequency, but in the Z transform this line part represents the what? The frequency characteristics. Okay, because we don't have the sampling time is going to 0 in this case. This is not a continuous, this is a discrete one. Okay. So in discrete domain we have only points. So the theorem 5.1 is simplified as to what? The xz is equal to z domain xt. This is a continuous signal, just remember that. Z x k t, t is a sampling period in here and k is a sequence number. Okay, and so this can be equals to the what? The k is equals to 0 because we have the 0 time, the first point, to sample the R signal, and so we have the infinity value, and x k t times z minus k can be written just like this one. Okay, for the sequence equation we can eliminate the t or the sampling period in here because it's a constant value at each time. Okay, and so this xz can be written as z x k t. Okay, this is equals to the what? K equals 0 to infinity value xk times z minus k. Okay, this is called the one-sided Z transform. Why is one-sided? Because we don't need to utilize the what? The minus infinity in here. Okay, and so if the sampling rate is constant, and now we can simplify the R algorithm as a sequence series, just like this one. But in the expansion form, we have the xz is equal to x0 plus xt times z minus plus x 2t times z minus 2 plus blah 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 xkt times z minus k. Okay, and so if the t is constant, and then we can replace this x continuous value with the what? With the sampled value. Okay, this is the basic representation of these terms. And so we have drawn the R representation just like this one in here. Okay, this is the x n, right? And so we have the 1 signal, 2, 3, 4, 5, 6, and goes on, this kind of information. Okay, and so this region is depicted with what? The z over 0 in here. Okay, and so this is the z minus 1, z minus 2, z minus 3, z minus 4, blah blah blah. Okay, and so this is our representation of what? The discrete time signal response. Okay, and so if we have the Z transform in here, just like this one, and if we have the dt is the constant, and so we can derive the transfer function or the pulse function to represent the dynamicity of these values, because we assign the time variable or the sequence variable at the what? At the over parts in here, just like this one. And so we have the 4 step forward in here. And so we need to use that z over minus 4, right? And so we can collect all the points in the one form in here with the multiplication with what? The z transform, just like this one. And so if we have any signal or any points in here, just like this one, if we multiply z over minus 5, and then we get, or we shift this formulation to the what? To the one form, the impulse form. Okay? Do you understand that? So if we have the what? For example, k equals to the 5, and so if we have this information, we don't need to go the k equal 5. If we have this information, and then we can apply the z transform with the terms of the what? The z over minus 5, and so this representation can be evaluated even if we have at the 0 time. Okay, by multiplying these z values with the what? With these nominations, and then we can collect the whole the points to the one point, which we call it to the what? The impulse response or the pulse transfer function in this domain. Okay, and so we can collect the whole points to the impulse. Okay, and also we can write the algebraic equation. Just remember the Laplace transform, S domain. For example, Hs is equal to the 5 divided by s plus 5. Okay, and so we can evaluate the signal based on this transfer function, right? And so this transfer function represents to the what? The final dynamicity of this system. And so this system governs or behaves based on this information or this characteristic, right? We have time constant, we have amplitude value in here, okay? But in the discrete time, we cannot use the s, right? Because we don't have the infinite zero sampling rate, right? And so if we have the different dt value or the bigger than 0, and then we should apply the z transform to represent the transfer function based on the what? The sampling period and the sequence number. This is how we can build the sequence number in here, just like this one. Just remember that we can evaluate the what? The Euler identity, just like this one, right? And so if we have this information, and then we can rotate the what? The 1 time, and so this is equals to what? The 1 hertz, right? And so if we second turn in here, just like this one, for the second turn we have the 2 hertz, right? At the 1 second. This is the same idea between the what? Between this domain, just like this one. For example, we have the 10 samples, or the simple meaning 8 samples. In the 8 samples, we have the what? 8 line. 1, 2, 3, 4. 1, 2, 3, 4. Okay? And so we have the 8 line in here. And also this is equal to the what? The z0. This is equal to z minus 1. It's equal to z minus 2. This is equal to z minus 3. This is equal to z minus 4. Z minus 5. Z minus 6. Z minus 7. And so z minus 8. Okay? But this is equal to what? Z0. Okay? In this domain, we have the z transform. Normally, we have the positive value in here, in the geometry. because in each iteration we forward going, but in the transformation, just remember the Fourier transform, we apply the minus operator in here. Just the same idea is given in here, and so the whole sequence can be represented in the what? In the Euler identity formula or geometrical representations. Okay, this is based on the what? The discrete Fourier transform 2. Okay, you understand right now? We can build or use this geometrical representation based on the what? The z over 1, 2, 3, 4, 5, and so each of the line can be created in here, and so we can evaluate the what? The behavior of the time response in the discrete domain. Okay, do you understand that? Okay, this is the geometrical representation, guys. This the simple discrete Laplace transform. Okay, we can evaluate the signal. For example, we have the examples in here, just like this one. Let's find Z transform of unit step function. The unit step is represent the xt 1 t is greater than 0 and 0 t smaller than 0. Okay, and so z 1 t or the unit step can be represented in here, can be deal with the what? The integration of the k is equal to 0 to infinity value 1 times z minus k, because it all the times represent what? The 1 unit step, right? If the t is greater than 0, and so this is equal to the what? The k is equal to 0 infinity value z minus k. Okay, and so this yield us in the z transform 1 plus z minus 1 plus z minus 2 plus z minus 3 blah blah blah. Okay, this solution can be done using the infinite series solution. Yield us to what? Z is equal to what? The 1 divided by minus z over 1. This converging to this value of this term. You may not to use the infinite series solution, okay, but you can do that. But this yield us to what? The z divided by z minus 1. Okay, this is our z transform results or the transfer function, but in what? In discrete time domain. Okay, this solution coming from the infinite solution. Just remember the math class. We have the balls is pull and push, then strike the ground and flip and flip and flip and flip and flip and flip, and so we can apply the what? The infinite series solution to what? To find out the converging values. This solution coming from the what? Converging theorem in that case. Okay, any question? Or we can define another examples in here, just like this one. Consider the ramp function like xt is equal to what? T greater than 0 and 0 t smaller than 0. Okay, and so this yield us to what? The xkt is equal to what? The kt, right? It's the ramp function k 0 1 2 3 blah blah blah, and so the z transform gives us xz is equal to zt, right? This is the t function, and so we can write to what? The k is greater than 0 up to what? The infinity value xkt times z minus k, and also it's written as to what? The kt z over minus k, And so this t is the left hand side of this equation because it's not dependent to k value. Okay, and so the k times z minus k. Okay, and so this is equals to the what? It's equals to t parenthesis z minus 1 plus 2 z over minus 2 plus 3 z 3 and blah blah blah. And so this yields us, by utilizing the infinite series solution, t times z minus 1 divided by 1 z minus 1 square, or in another term, t multiplied the z and z minus 1 square. Okay, and so you can easily check the z transform table to find out another important function solutions. Okay, this is how we can analyze the time series signal or the sequence of the signal in the z domain. Okay, any question? If you don't have any question, you should take a break for 15 minutes.